Here we are with Unit 2. Taking a look at the student learning map. Unit essential question, how do I find the area under a curve? Actually, area between the curve and the x-axis would be a better way to say that. And the first concepts we're going to take a look at, 211, 212, are piecewise and periodic functions. So today we're going to take a look at how can transformations of functions be utilized to graph piecewise and periodic functions. So we're going to learn a little bit about what that means. Today specifically, we're going to learn about piecewise functions. So what if it is in pieces? Okay, here's a little historical note, okay, that you can look over if you need to. All right, and just to read a little bit about what that means. Up until this point, we've always graphed just one equation, a piecewise function. Okay, we've never graphed one whole function. We've never graphed a piecewise function where we're only looking at pieces of functions and not the whole function. Okay, so here is a math notes box. This will be good to put into your math notes. Okay, sort of a good definition, where this should look familiar because we did this with inequalities in algebra. All right, where we looked at a system of inequalities or a system of equations. This right here would be your domain restriction. That tells you what you're graphing, or excuse me, this tells you what you're graphing. The domain restriction tells you where you're graphing it. Okay. So problem 2-1 says let f of x equal x squared plus 2 when x is less than or equal to 2, and 1/2 x plus 1 when x is greater than 2. With your study team, investigate this function thoroughly, just as you have investigated any other function in the past. Remember, all the aspects of investigating, make a careful sketch, so on and so forth, yada, yada, yada. So we're going to do that right now. So taking a look at this piecewise function, we're going to graph this parabola piece, x squared plus 2, when x is less than or equal to 2. So my advice here would be, one, you could do this in your head by hand if you'd like to, using graphing transformations. If you're a beginner and you don't feel very comfortable with this, then I would make a table, okay? And that table is going to start with an x value of 2. And it says when x is less than 2. So less than 2 would be 1, 0, -1, -2. All right? And then you find the corresponding y values for those x values, and you only plot those points, and you only draw that piece of the graph. Okay, so if x is 2, 2 squared is 4, 4 plus 2 is 6, so over 2, 1, 2. There we go. Okay, if x is 1, 1 squared is 1, 1 plus 2 is 3. If x is 0, it's 2, because the vertical shift of 2, and then it reflects. So my graph would look like this, where it would continue on forever in this direction, because x can be less than 2, but it can't be anything bigger than 2, so that it actually comes to a stopping point right here. Then you graph the second piece of your function. In this case, it's linear, and it says 1/2 x plus 1 when x is greater than 2. Again, same idea. You can make a table if you'd like, and we're choosing 2 is still the endpoint. Even though it says greater than 2, all that greater than symbol does is tell us what symbol to use on the graph, what kind of dot, open or closed, okay? But we still want to use 2 as the endpoint. A lot of people see greater than 2 and they think the first point they're going to plot is 3. That would be wrong, because you have 2.1, 2.2, you have 2.11, you have 2.01, you have a lot of points in between 2 and 3 that work also. So we want to start at 2. We're going to use an open circle at 2 because it's just greater than, not greater than or equal to. All right, so if I plug a 2 in, that's 1. 1 plus 1 is 2. So right here, I would have an open circle, and my slope is up 1 over 2. And I would draw my line. Again, it goes on forever in this direction because x can be greater than 2, but it cannot equal 2, and it can't go less than 2, so it has to come to an endpoint right here. I use an open circle to symbolize the fact that, and you should know that from algebra and doing inequalities, that means it cannot actually equal 2, but the very next value after 2 is okay. That's a piecewise function. Again, piecewise because we have 2 separate pieces that make one function. Is it a function? Does it pass a vertical line test? Sure thing. Even here where it looks like it might overlap, we have a solid point and an open point, so it does not overlap. Problem 2, let us look at an application of a piecewise function. Lisa makes $4 an hour babysitting before midnight, $6 an hour after midnight. She begins her job at 7 p.m. Complete the table for the total amount of money Lisa makes. Okay, so let's see here. At 8 p.m., she's been babysitting for 1 hour, so she's made $4. At 9 p.m., she's been babysitting for 2 hours. Well, if she makes $4 an hour, that means it's going to be 4 times the number of hours. So that means here she would have made $8. Here she would have made $12. This is kind of confusing here because it's missing the actual 11. Okay. But at 11:30, if you plug 11 and a half in here for H, okay, if you plug 11 and a half, 44, it's going to be $46. But then once she gets to midnight, she's making $6 an hour after midnight. Okay, so once she gets to midnight, now it's $6 an hour, plus what she had made before. Okay, so here at 5 hours, it's $6 an hour, which is 6 times 5 is 30, okay? But it's only $6 an hour for each hour after midnight. All right, so up until midnight, she's made $4 an hour. So, I screwed that up here. Hold on, sorry. She went from $12 to $46. What are you doing, Mr. Warner? Okay, sorry. 11:30 is 3.5 or 4.5 hours after 8. So it would be 4 times 4.5. Sorry about that. Okay, so that would be $18. Okay. At midnight, it would have been $20. So she still makes $20 up until midnight. So right here is 20. Okay. After midnight is $6 an hour though. Okay, so at 12:30 she made $3 in that half hour. So it's the $20 from before plus the half hour here, which would be $23. And then it's 20 plus the 6 here, which would be $26. And 20 plus 2 times 6 would be $12, would be $32. Okay, so that's what your table would look like. If you wanted to fill in entries after midnight above the table, we need to realize that the function is piecewise. That means she's getting paid 2 different rates. Okay, so from 0 to 5, the equation is simple. It's 4h, or in this case, sorry, they use x, so let me use x, 4x. But after 5 hours, it's 6x plus, and this is how much money she has at that midnight mark, or at that 5 hour mark, which in this case was $20, so we got to put that in there. Because she doesn't lose the money she made before, but she doesn't make $6 an hour on that money afterwards, okay? So that's what we're looking at there. Let's see here. Rules, okay, there's one more thing we need to throw in here, because if we just plug in 5 or 6 or 7 for x, that's going to add $6. That's going to make $6 an hour for every hour she made before that too. So we actually have to put an addendum here. Okay, it's x minus 5 plus 20. Okay, because we can't give her credit for the hours she worked before that 5 hour mark. All right, so we got to take the number of hours and subtract the 5 hours she already got credit for, which is where the 20 comes from, and then times it by 6. That's a tricky problem. Okay, so key ideas, chapter 2. I'm not sure why that's there. That should be at the end of the chapter. Here's another piecewise function. Fill out the table. I told you, table's where it's at. Okay, so x squared plus 2, and 2x plus 7. And then we're going to make a careful sketch of that, so on and so forth. So again, you can complete the table if you need to, or you can do it by hand. It doesn't matter to me. But here's your first function, x squared plus 2, which is the same one we did before. It's a parabola moved up to, starting when x is 1 and for everything less than that. Okay, so if I was going to graph that parabola, 1 squared is 1 plus 2 is 3. Okay, 0 is 2, it reflects. 2 is 6. So again, it's a parabola that goes on forever this direction, because it can be less or equal to 1, but it stops at 1. Then you graph the second portion, which is a 2x plus 7. Okay, and that's linear. So I plug a 1 in. Again, 1 times 2 is 2 plus 7 is 9. That's an open circle because it cannot equal 1. All right, but everything greater than 1 works, so up 2 over 1. Okay, and it's going to look like that. So there's your piecewise function. Again, goes on forever this direction, but stops at that value, which is 1. What's the domain and range of this function? We do that no different than you did it before. The domain will be all possible x values. which in this case is negative infinity to infinity. Okay, you could also write the domain as all real numbers. All right, that's a little shorthand version of saying negative infinity to infinity. Well, what about the range of this function? That's all the possible y values. So again, you're looking at the whole function. You're treating this all as one here, okay? So the lowest it goes is right here. That's the lowest it goes, which is 2. And it does actually hit 2. How high does it go? Well, this says it goes on forever. So does this. So range would be 2 equal to, and then infinity. All right? Or you could write it as all real numbers greater than or equal to 2. I would accept either of those for your range. No x-intercepts. One y-intercept. And I believe, I don't know what that is. Okay, using technology to graph piecewise functions. You can read through this in your book and see if you can type it into your calculator. It's kind of tricky with the 83s because it won't leave a blank. In other words, the last graph we did should look like this. Okay, but just like your 83, you know, it's not supposed to graph an asymptote either, but it does, so it actually looks like this. Well, piecewise, it does the same thing. If you're doing a piecewise function, it's going to look like this. And it connects them, which is not true. Okay, so it's not the best calculator for that. If you have the 84, that would work better. And that's for section 2.1.2. Sketch or use your calculator to make a graph of this piecewise function. So again, we're right back to the same as before. All right, let me get a grid here. Find the domain and range of the function. Okay, is the equation continuous for all values in the domain? So 2 to the x when x is less than 2. Again, you can use a table if you'd like to. All right, I have no preference. All right, you can make a table, start at 2, 3, 4, 5, whatever. Okay, but when x is less than or equal to 2, so 2 squared is 4. 2 to the first is 2. 2 to the 0 is 1. And we know what that's going to look like. It's exponential. It has a horizontal asymptote here. Okay. And then when x is greater than 2, I have a linear version of that same graph. So negative 2x plus 9. So at 2, 2 times 2 is negative, 2 times negative 2 is negative 4 plus 9 is 5. So right here I have an open circle because it's just a greater than symbol. And then 3 times negative 2 is negative 6 plus 9 is so down 2 over 1, down 2 over 1, and I get this. Okay, so there's my piecewise function. Again, open circle for this portion because it's just a greater than. Okay, and closed circle for this portion because it does actually equal to. So I have, this has part of an asymptote. It can't continue because it does actually equal this value. And then it has a linear section here. So we have an exponential section, a linear section. Again, piecewise function. Pieces of functions. All right, is it continuous for all values of the domain? We don't really know what continuous means yet, but you can see right here it breaks. So I could not draw this graph without lifting my pencil. I would have to lift my pencil to get to here. So that would mean it's not continuous on the whole domain. The domain here is all real numbers. Okay, you could also say negative infinity to infinity. The range would be all real numbers that are less than or equal to this highest value, or actually it wouldn't be equal to, sorry about that. It would just be less than this y value right here. So that is 1, 2, 3, 4, 5, 6. Okay? No, 5. 5, sorry. Okay? So all real numbers less than 5. And there's some math notes on what it means to be continuous. We'll talk more about that in section 2.1.2.